2014.
Thank you very much. Good afternoon, everybody. Okay, just one reminder, the midterm will be March 7, which is tomorrow, Salvatore 101. Everybody familiar with the room? Salvatore 101 from 4 to 6 and 6 to 8. Your choice. You don't need to tell me. You just come whichever one. But always keep in mind, if you come at 4 to 6, you cannot leave early. You cannot. You have to stay till the end of the exam. Okay. I will have office hours in my office from 11 a.m. to 3 p.m. tomorrow. I will be around, by the way, I might even be before that, but I cannot be sure. But I will be around 11 a.m. to 3 p.m. After that, I need to go and pick up exams and stuff like that. Clear? Clear? Okay, good. Now, and today's lecture is not, today, by the way, I will be struggling very badly. I have a very sore throat here, so bear with me. Today, sorry, it's a lecture is not included. Okay, which means what? It will be show up in where? In the final. Okay, now, and this is the last set of charts before we get into the circuits portion. Remember, the course has what? Half circuits, half system, half circuit. This is the last set of charts on the what? On the systems aspect, which means what? After the midterm, we will start with the what? With the circuit. And that's where it gets a little bit what? Messy. Clear? So, but I need to introduce you to the modulation techniques that are used in the real world. Now, this one here is a material of EE 564 and EE 535. However, we will go much deeper than they do. You follow me or not? Because we don't care. So we go much deeper than they do. So we need to understand. However, you need to understand is that we are not going to get into what? Heavy analytical stuff here. Clear? Not, but I need you to understand the trade. Most important thing to me is the trade. In other words, when you are given the responsibility to choose a given modulation technique, which one to choose and why? What are the parameters? What are the things that you need to take into account to choose the modulation technique? Clear? Okay. Now, first of all, quick review. Can you zoom back, please, a little bit, just a little bit? Thank you, sir. Let's look at the modulation. We already discussed this. Let's see if you still remember. What is, I have a what? What is this? Tell me. Baseband. Why? Because the spectrum is centered around what? Around 0. Most of the frequency components are what? Low frequency components. Are you following or not? I'm going to apply it to a what? Generically, I call it what? RF transmitter. The RF transmitter will translate the spectrum from what? Baseband to what? To RF. So this one is centered around what? Centered around omega, sorry, what is this? F? So F sub C, or F sub O. Clear so far? Yes or no? Now, a little bit misleading, this diagram. Why? Because it gives the impression that the modulation is basically frequency conversion. Do you understand that? No, frequency conversion means what? You just, the same spectrum, you just push it what? Upward. That's not necessarily the case. The case might be what? It may be that with doing modulation, you are going to create what? You are going to create multiple what? Sidebands that were not available in the original spectrum. Clear? Okay. The only thing that I need to understand right now is that modulation is not a linear operation. Why is it not a linear operation, or the modulator in general? Why? Because a linear system does not introduce new frequency components. Are we introducing new frequency components? Of course, that's the whole idea behind it. Clear? So keep that in mind. At the receiving side, we will do exactly what? The opposite. In the demodulation, we are going to what? Translate the spectrum from around the RF to what? To the DC. Notice, by the way, the translation or the conversion back could be done in what? In multiple steps. For example, in the heterodyne receiver, you are going to go through what? Through to the IF. By the way, even the IF, you could have what? Multiple IF stages. Clear? Okay, before you get to the DC. If it is direct conversion, then you will go directly from RF to DC. Okay. Now, let's see if you remember very quickly the reason for modulation. Quickly. The first one, most important one of them all, actually, is what? Is that the size of your antenna is what? Is inversely proportional with the frequency of radiation. Did you get my point or not? And if you are going to be transmitting at low frequency, the antenna will be extremely what? Extremely high. Are you following or not? Extremely large. Sorry, I said high. Extremely large. Clear? Remember, the area is inversely proportional to the what? To the lambda. Lambda is what? Is the wavelength. Agree? Okay. Another example, which is another reason which is equally important, is to allow multiple access. Is to allow multiple what? Multiple sources to be transmitting at the same time. Especially for what? Direct broadcast, radio broadcast, TV broadcast, and so on and so forth. If they all occupy the same baseband, they are not going to be able to what? Transmit at the same time, because they will be what? Overlapped in time and what? Frequency. So you do what? You do the modulation into what? Into different carriers to result in what? Result in the spectrum being different, non-overlapping. Clear? Modulation is done in every wireless system. Every wireless system there is, whether it's cell phones, whether it's AM, whether it's FM radio, whether it's wireless LAN, even, by the way, cable TV does not have to be wireless. In cable TV, do we need modulation? We need modulation. Over-the-air TV, do we need modulation? Modulation is there. No other way around modulation. Clear? Okay. Now, what we are going to do is what? We are going to spend very little time on analog modulation, and the rest of the time is on what? Digital modulation. But I want you to understand, what do people mean when they say analog modulation or digital modulation? The output of the modem, remember, how many inputs does the modem have? 2 inputs. So we have this. This is called what? The information signal. Another name. The modulating ing. The modulating signal. Another name of it, of course, is the what? Is the baseband signal. Clear? The baseband signal. And then I have the what? Carrier signal. And I get what? I get the modulated carrier. Clear? Answer me the following question. Is this digital? This is an analog signal. So the question is what? Why do we call it digital modulation? When you talk about digital modulation, what does it mean? It means I have a what? An analog signal carrying what? Digital information. It means the information is what? Is digital. But the signal being propagated is always what? Analog. Did you get my point or not? Now, is it possible that the source is analog? If the source is analog and you do not convert it to digital via the use of what? A to D. A to D stands for what? Analog to digital converter. Then what do we call the modulation technique? Analog modulation. So in analog modulation, the information signal is analog. the modulated carrier is also what? Analog. We call it what? Analog modulation. In the digital case, the information is what? Digital. Either digital by nature or digital by what? Digitizing a what? An analog signal using the A to D converter. Did you get this or not? We call it what? Digital modulation. Now, let's see if you still remember. What is the mathematical model for a carrier signal? Mathematical model. A, C of T. C stands for carrier. Is what? A cosine. What are the parameters? The parameters are the amplitude and the frequency and the what? And the phase. Are you following or not? Modulation, all of them, by the way, are they constant? All of them. They are all constant. They are all fixed. Clear, fixed amplitude, fixed frequency, and fixed phase. At least what? At least theoretically. Especially the frequency is a big question mark. Why? Because who is generating this? Who is generating this guy? An oscillator. And an oscillator, when we get to the oscillator, we will see that the oscillator is not going to be a what? A pure, clean oscillator. Clear? Okay, good. Now, how many parameters does it have? 3 parameters. The amplitude, frequency, the phase. Modulation is the process of what? Altering or changing one of these parameters, one or more of these parameters in accordance with what? With the modulating signal. So we have what? In the analog modulation, we have the usual suspect. This is the usual suspect, which is what? The AM. AM stands for what? Amplitude modulation. FM, which means what? Frequency modulation. And PM, which means what? Phase modulation. Now, when I show you the curves in just a second, you will see that for analog modulation, you will not be able to tell me what is the difference between FM and what? PM. In other words, when you look at the signal and somebody asks you, is this an FM signal or is it a PM signal? You will tell them what? I cannot tell them apart. Did you get this or not? Yes or no? Okay, we'll see that shortly. Whereas in digital modulation, you can tell what? You can tell apart very easily. Now, in digital modulation, what do we have? We have the binary schemes, which is what? The binary amplitude shift keying, binary phase shift keying, binary frequency shift keying, binary what? Phase shift keying. Let's stop in here for just a second. Do you remember what do I mean by binary? In a binary modem, every bit goes, did we talk about this earlier or not? Did we do? In this course? Okay. In binary modem, every bit goes in, a signal goes out. Which means what? The signaling rate in binary modem, the signaling rate, RS is equal to what? RB. This is the signaling rate. Clear so far? Okay. These modulation techniques, the binary case is on their way what? I mean, you know, it's not as widely used as what? As it used to be before. Why? Still waiting. Why? Still waiting. Why? It's because it does not provide for what? Higher bit rate. Remember, the signaling rate is limited by the what? By the bandwidth of the medium. Are you following me on that? The bandwidth of the medium. So you are not going to get higher rate using what? Using binary modems. Clear? Okay, good. But is their performance good? Their performance is better than the multi-level. Are you following me or not? But on what expense? On the expense that it is what? It is slow. And what do you expect? If it is slow, if you are transmitting slowly, chances of errors increase or decrease? Decrease, which means what? The performance becomes better. But you are very slow. Did you get my point? Okay, good. Now, then we have, of course, QPSK, which is what? Which is the quadrature phase shift keying. Clear? Which is widely used, even now widely used. In this case here, how many bits goes in? 2 bits goes into the modem, 1 bit goes out. Which means what is the relationship? RB equal to what? 2RS. Or RS equal to what? RB over what? Over 2. There are multiple variations of the QPSK that we will study. The most important one of them are these two. OQPSK stands for what? The offset quadrature phase shift keying. And the other one is called what? Pi over 4 QPSK. You might tell me, Professor, what is pi over 4 means? I will show you that in just a second. Clear? Anybody here is taking 535? Did you go through this or not? Okay. So, if the pi over, we should know what pi over 4 QPSK, I assume. Okay, good. Now, but I will show it to you shortly. Then there is the what? There is, by the way, all of these this one, not this one, this one are regarded to be what? Non-constant what? Non-constant envelope. Now here we need to stop for a little bit, a while, and answer the following question. In QPSK, what parameter am I changing? I am changing the phase. Are you following or not? So you might say, why is the amplitude not constant? During the what? During the symbol duration, the amplitude is constant. The problem, what happens in what? In the boundary between the what? Between the symbols. Going from one symbol to another symbol, there could be a what? There could be a 180-degree phase shift. And when it is 180-degree phase shift, what does it mean? It means you go from a what? Positive to what? Negative or what? Vice versa. Did you get this or not? During that time, we are in trouble. Clear? We are in trouble. Because when the amplitude reaches 0, what does it mean? It means the receiver will not have the ability to detect the signal. Will not have, because it's 0. Clear? Okay. But we'll get to that in a minute. Then we do have two types of what? Two types of modulation technique that was adopted for GSM. GSM stands for what? The Global System for Mobile Communications. And again, you will take this one in the 535, I assume. Okay, these two techniques are called what? MSK, which is what? The minimum shift keying, and the GMSK, which is what? The minimum shift keying with Gaussian filtered data. What is Gaussian filtered data means? I am going to what? Shape the data. Shape the data in a what? In a Gaussian format. Question. What can you tell me? Do you know what a Gaussian? Yes or no? What is the property of a Gaussian distribution? No. I know it's a zero mean. But what is it smooth or is it sharp? It is smooth. Are you following me or not? It is smooth. And once, remember always, when the signal in the time domain is smoothly changing, that implies what? It implies that the side lobes will become what? Lower. Are you following me or not? Why? The spectrum will become more compact rather than what? Rather than widely compact. Did you get this or not? What is the spectrum of a square pulse with no shaping? With no shaping. It's a sync type, which keeps what? Keeps going on and on and on and on and on. Whereas this one, we will see that the bandwidth or the spectrum is more what? It's more compact through the shaping of the signal. Wave shaping, by the way, is an integral part of any design, of any our receiver design. Clear? Wave shaping. But the wave shaping is done where? Not wave shaving. I said wave shaving. I'm sorry. Wave shaping, not shaving. We are not shaving here. Where it is done? Where it is done? It is done in the baseband, in the back end of your receiver, not at the RF section. Did you get this or not? So it's mostly the responsibility of who? Of the systems engineer rather than the what? Rather than the RF engineer. Did you get my point or not? It is done in the baseband. Okay. Now, then we do have what? We do have the generalization of this, which is referred to as what? The MPSK, which is the multi-phase shift keying. And then we will study also the what? The QAM, which is what? Quadrature amplitude modulation. And of course, we finish it with the overview. I need to give you an overview of what is known as what? OFDM. OFDM stands for what? Orthogonal frequency division. Do I need to write what FDM stands for, or you know? FDM stands for what? Frequency division, multiple access. Sorry, multiplexing. Orthogonal frequency division, multiplexing. Clear? Okay. This is the technique that is used in what? That is used in the newer generation of our cellular systems, of the local area network, wireless local area network, and so on. So, now, I'm not sure if this is a part of 535. I'm not sure. However, I will give you enough of it to be able to what? To talk with people about it, to discuss it in interviews, and so on and so forth. I don't want you just to say what, FDM stands for orthogonal frequency division multiplex, and then they would tell you what does that mean? You tell them, I don't know, next semester. I don't want you to do that. Clear? So I will give you an overview on this one here as well. Okay, let's start with the simple one, which is what? Amplitude modulation. I don't want to spend too much time on this, but I want to bring a very important parameter, which is called the power. A very important R parameter is called the what? The power. And the power stands for what? The peak, the peak to average excuse me, the peak to average power ratio. But first of all, let's look at it briefly. First of all, always remember, learn about, even though it is not an RF engineer point of view, it's more of a systems engineer, but learn how do you write the mathematical model for what? For this modulation technique. Clear? It helps you visualize how is everything is being done. So in AM, this is the signal. X of t, what happened? X of t. Did we call this one S of t or S of t? 1 second. What did we call this? S of t or X of t before? Anyway, it doesn't matter. This is what? Which is what? That's A1 plus mu. I'll explain to you what mu means in just a second. M of t cosine. Can I write instead of 2 pi FCT, can I just write omega c for simplicity? Or will you get depressed? Can I write omega sub c? It's easier for me than to keep writing the 2 pi stuff. Okay, so it's what? Cosine omega ct plus some theta. Arbitrary. What do you notice? Where is the modulating signal? The modulating signal, M of t. Did you get my point or not? If M of t is 0, if there is no modulation, what do you receive? What do you end up with? If there is no modulation, which means what? M of t equal to 0. What do you end up with? A cosine omega ct plus what? Theta. Which is the what? Which is the carrier signal. Yes? Cannot hear you. Question. How much was the power of the carrier signal? Just the carrier signal. Just the carrier signal. Not the modulated carrier. Just the carrier signal. How much was it? It's a square over 2. That's the average power of a carrier signal. Did you get my point or not? Yes or no? Okay. Now, what do I want right now? I want to what? To take the power from the what? From the carrier component and put it in where? In the information signal. And the signal that is what? That's actually carrying information. Keep that in mind. Okay. And what is the mu? By the way, what is the maximum value of cosine? What is the maximum value of cosine? Maximum value of cosine is what? Now, if we assume that absolute value of M of t is equal to what? 1, which means what? What am I doing? I'm normalizing the information signal. Yes? What is the peak value of this? What is the maximum value of this? So the maximum value of X of t will be equal to what? I'm still waiting. A times what? Mu. You agree? Yes or no? What is the minimum value? Again, the M of t is what? Absolute value of M of t equal to what? Is normalized to 1. Clear? Well, the minimum value is when cosine is equal to what? when M of t equal to what? Equal to -1. When we say absolute value of M of t equal to 1, it means what? It could be -1, which is what? Clear? Oh, what is the mu? What do I call the mu? Anybody? The mu is called the what? The modulation index. And what is the modulation index equal to? How would I define it? It's the maximum value minus the what? Minimum value divided by what? Maximum value. When I say maximum value of who? Maximum value of who? Maximum value of the modulated carrier. The output from what? The output of the modulator. Maximum value plus what? Do you see that this one will give me mu? Let's see. A plus a mu A minus A plus a mu A. So what do you get? 2 mu A. And in the denominator, what do you get? You are adding, you get what? 2A. So 2 mu A over 2A equal to what? Equal to mu. Clear so far? Yes or no? Cannot hear you. Now, if I remove this 1, Do you see this one? If I remove this one, in other words, if x of t is written as a m of t cosine omega ct plus what? Theta. What did I assume here? When I wrote it like this, what did I assume? I assumed what? That if x of t, yeah, what did I move? Sorry, I forgot the mu. There's a mu here. What did I remove? I remove a 1. What do I call this? What? Oh, tell me, first of all, listen to me. Listen to me. Which component did I move away? Get rid. The carrier component, which means in the spectrum, I'm not going to have a what? An impulse, a discrete component at what? At omega sub c. Yes or no? What do I call it? Anybody? DSB SC. What does DSB stand for? Double sideband suppressed carrier. Double sideband suppressed carrier. Now, answer me the following question. Let's see if you can answer me the following question. Which domain is this? What am I multiplying? What am I multiplying? I am multiplying a fast-changing carrier signal. A fast-changing carrier signal by a what? A slowly varying signal. Why? Why is this one slowly varying? That's a baseline signal, a voice, a video, or whatever. It's a slow signal for low frequencies. I am multiplying it, I generate this. Can you tell me what do I call this? Look at me, this one, the dotted line. Do you see the dotted line? What do I call it? That's the envelope. And what do you notice? You notice that the envelope resembles the who? It resembles the modulating signal. Are you following on that? Which means what? If I can recover the what? If I can recover the envelope, it's what? I am recovering what? The modulating signal. Did you get this or not? I want you to see one thing here before I show it you in detail. Let's take an example. Just an example. And this is what? This is T, and this is what? The M of T. Now, I'm going to what? First of all, I'm going to push it by what? 1. Yes? Yes or no? So what do I get? Clear? Okay, I should not have sketched this on the same diagram. Right now I'm stuck with this one in the middle. But let me sketch it again. I made a mistake. Okay, where is the signal? Where is the carrier signal? Carrier signal is you got my point here. This is not Picasso. Did you get my point? Clear? Yes or no? What is this called? Is the envelope the same as the modulating signal? No, it's not. It's shifted up, which means if I recover the modulating, if I recover the envelope, listen to the question. If I recover the envelope, how do I recover the modulating signal? I need to put a what? I need to put a DC blocking capacitor. Why? A DC block capacitor means what? That shift in here will be what? Eliminated, and this one will go what? Will go down again. Did you get my point or not? Yes or no? No response. Yes or no? Okay. Now I want you to see something. What if I don't push it up? What if I don't push it up? Can I still use envelope detection? Let's see. How does it look like? How does it look like? If I don't push up, so the spectrum is like what? Yes? I don't push it up. Now, help me. Where's the other side? Agree? Okay. And where is the... Clear so far? Clear so far? Where is the envelope? Can you show me where is the envelope? I'm still waiting. Where is the envelope? Remember, the envelope is a what? It's the positive. It's the absolute value. So where is it? Agree? Does that resemble the modulating signal? Does that resemble the modulating signal? So what is the first conclusion? What do I conclude at the beginning? If I'm going to use what? Double sideband suppressed carrier. If I'm going to use double sideband suppressed carrier means what? I'm not going to send the carrier signal. I cannot use what? The simple envelope detection in this case. I cannot use the simple envelope detection. Are you following me or not? I can only use the envelope detection when I'm using what? When I'm using the AM modulation, the general one. Yes or no? When will the amplitude, can you tell me, when will the envelope resembles the modulating signal? When I push this one up by how much? Or what do I need to ensure? I need to ensure that there is no what? Negative part remaining. In other words, push the spectrum up such that there is no what? There is no negative part remaining. Once there is a negative part remaining, it means the envelope has been what? Has been distorted. Clear? Now, what is the envelope detection? Cannot be used or coherent demodulation of AM signal. That's all. Double side. Clear? What is so special about the envelope detection? Have you heard about envelope detection? What is so, which class? Okay, you forgot. And once you forgot, what does it mean? It means when you were a kid. So you forgot. But what is so special about it? It's a very simple circuit. This is the envelope detection. Clear? What is this? Diode. Why? Why do I need the diode? Why do I need the diode? Remember, the envelope is everything which is what? On the top. So the diode is going to get rid of what? Getting rid of these. Did you get this or not? Now, if the input is positive, what happens? The diode will conduct because it will be what? Forward bias. The capacitor begin to what? Charge up. Yes or no? If the input becomes what? Negative, this one will become what? Open. Yes or no? And what has happened to the capacitor? Capacitor will discharge through what? Through R. Clear? What is it? Sketch it for me. Sketch it for me. This is positive, so what do I have? Slope. Sketch it for me. It's too close. Are you following me or not? Yes or no? Close enough or not close enough? Close enough. Are you following me or not? This one, by the way, let me ask you a question. What is this? What is this behaving as? That's a low-pass filter. Are you following me or not? Low-pass filter to smooth the what? To smooth the edges. Did you get my point or not? Hard or easy? Easy. Are you following me? This is your AM radios. AM radios, this is the what? This is the detector as the receiver. Clear? Now, then what is for DSB, SC? What do I need in here? In here, I need to have what? I need to generate a coherent what? A coherent carrier component at what? At the receiver. Which means I need to have what? Some kind of a what? Some kind of a phase lock loop. Did you get my point or not? Yes or no? A question, by the way. This one here, this carrier. Can I use, by the way, can I use coherent detection with the AM signals? No, I mean, I don't want to use the envelope detector. Can I use the more advanced? Of course you can use the more advanced. Are you following me or not? Okay. The beauty also of the AM, just regular AM, is that when you are transmitting this carrier component, that carrier component will help the receiver generate a what? A locally generated carrier, which is in synchronization with what? With the carrier that you are setting. But what is the problem? What is the problem? The problem is that you are going to waste power transmitting a what? A carrier component that carries what? That carries no information in it whatsoever. Clear? Okay. Now, let's get back to the charts and try to understand a little bit better. Answer me the following question. What is this? I am multiplying in which domain? In the time domain. Multiplication in the time domain corresponds to what? Convolution in the frequency domain. What am I convolving? I'm convolving the spectrum of this guy, which is this guy. Yes or no? Okay, that's the baseband signal with what? With the spectrum of this guy. What is the spectrum of this guy? Two impulses at what? F sub C and minus F sub C. Yes? What do you get by convolving a function with an impulse? You get the function shifted toward where the impulse is what? Located. Do you still get an impulse? I'm not sure did you get my point. When you convolve a function, f of x, for example, convolved with what? What do you get? So what is it mathematically? Can you give it to me? Verbally, you are telling me a right answer. Can you give it to me? F of what? X minus x0. And my question to you, is the delta still there or not there? Not there anymore. When you modulate, when you multiply with the delta, what do you get by multiplying f of x times delta, x minus x0? What is this equal to? F what? No. Times. I think you lost me here. Did you lose me? Multiplying a function with a delta function, what do you get? You get a delta function, same delta function, but it will be scaled by the value of the function where the impulse is what? Located. Whereas if you convolve a function with an impulse, you just give it what? Just simply shifting a what? Shifting the spectrum towards what? Towards F sub C. Clear? Okay. Let me ask you a question here. Is this spectrum the same as this spectrum? This one and this one. Is it the same? They are the same. They are just what? Converted up. Which means what I told you a moment ago, that this is a little bit what? Misleading by saying what? By saying this is spectrum. It's not in AM. In AM, this is actually the spectrum that you will get. Did you get my point or not? Okay. What is the bandwidth? What was the bandwidth of the baseband? The bandwidth of the baseband was what? Let's say B. What is the bandwidth of the baseband? Of the passband? And that's the first problem of what? Modulation. Modulation resulted in what? AM modulation resulted in what? Doubling the what? Doubling the bandwidth. Now, the information, assuming this one is what? Assuming this one are what? Are symmetric. Then the information in the, what do we call this? By the way, listen to me. Is this double sideband suppressed carrier or is it conventional AM? It's not conventional AM. Why? Because if it is conventional AM, what would I see? I see a carrier component represented by what? An impulse at F equal to what? F sub C. Do we agree? Yes or no? Coming from where? Which term? Can you tell me coming from which term? A times what? 1 times what? Cosine omega C. Yes or no? So this one is a suppressed carrier because you don't see any components here. Clear so far? Yes or no? Okay, good. Now, next. What is coherent? This is the AM coherent reception. What this coherent tells you. This is the receiver. What is coherent? This is the received AM signal. Yes or no? Okay, what am I doing? I am what? Mixing it with a what? With the carrier signal. But what does that imply? This has to be the same as what? Same frequency and what? Same phase. Did you understand that or not? The phase error should be very small. Clear? Clear? Easily achieved or not easily achieved? Very hard to achieve. Why? These oscillators are located what? Are located far away from each other. Not necessarily the same place. Clear? Okay. Synchronization, by the way, you take it in another course. Which has not been offered for the last 20 years. I have no idea why. To tell you the truth, it's mind-boggling to me. It used to be one of the most popular classes at SC. It's synchronization. It's called synchronization techniques, phase lock loop design and stuff like that. Suddenly, it's what I think the professor who used to teach it maybe has retired or something like that. So it's you know, not offered anymore or any consistency or something like that. One more time, what is the penalty paid? Increasing the what? Bandwidth. The information in the upper sideband and the information in the lower sideband, are they identical? Do they have to be identical? In this case, they are. But in reality, when we get to the digital modulation, when we get to the IQ, we will see that that's not necessarily the case. Did you get my point or not? Okay, good. Now, if the information is the same, can I filter one of them? What do I get? Instead of the double sideband, I get what? Single sideband. Did you get my point or not? But on what expense? On what expense? On the expense that I need to design a what? A very sharp filter. Are you following or not? Centered where, by the way? Is the filter centered at F sub C? No, the filter is like this. Clear? Sharp edges or not sharp edges? Sharp edges. Why? To prevent the lower sideband from getting in. But the sharp edges implies what? Implies that the impulse response, which is h of t, is what? Is non-causal. The system will become what? Non-causal. You cannot what? You cannot build it. Clear? Okay, good. Now, let's look now at the coherent modulation. In the coherent modulation, I'm using what? A coherently generated. A coherently. When you hear the word coherently, what does it mean? It means it's synchronized in both the frequency and the what? And the phase. Clear? Okay. Now, we will talk about this later on when we study how we design phase lock loop, both analog and digital, later in the semester. Now, if you multiply this with this, what does it mean? Analytically, what does it mean? Can you tell me analytically what does it mean? I'm going to multiply this with another cosine. Yes? What do I get? Cosine square. The cosine square is what? Is 1/2 plus 1/2 cosine twice the angle. Yes? The first term, which is 1/2, will be multiplied by this. Did you get this or not? That is what you are after. That is what you are trying to recover. Agree? What about the second term? What about the second term? The second term will be what? This multiplied by what? Cosine to omega ct, which means what? Another modulation, but on which harmonics? On the second harmonic rather than a what? On the first harmonic. Of course, after the mixer, what do I need? I need a filter. Are you following me or not? I will use the filter that will what? That will filter the sum. So I'm sorry, the difference rather than the what? Than the sum. Did you get this or not? So all of this second harmonic will not have any effect on my. I will not have any effect on my system. Clear? Okay. Now, the next one. I need to explain to you this very carefully so that you understand it. A lot? Yes. This is cosine that is coming from where? Here is cosine. This one has a cosine. What is this? Give me the mathematical model for this one. One more time. What is it? It's A times what? 1 plus U M of T times what? Agree? What am I multiplying it with? Another cosine with exactly the same what? Frequency. So what do I get? Cosine square omega ct. Yes or no? And cosine square is what? Is 1/2 plus 1/2 cosine the angle. Clear? Clear? Okay, good. Now, let's understand this concept, which is the power. Peak to average power ratio. Answer me the following question. Which modulation listen to me. The higher this parameter is, what is that an indication? The higher it is, what is that an indication of? It is an indication that the envelope is what? Is not constant, which means what? It's changing. Are you following or not? If this happens to be close to what? 1, what does it mean? It means that the amplitude is what? The amplitude is relatively what? Constant. Clear? But how do we define it? Listen to how we define it. So the power is the peak power to what? Average power. Answer me the following question. Which one is easier to measure in the lab or something? Average power is much easier. Why? Because in an average power, I am looking at a what? I'm looking at a long period of time and I'm measuring the power. Whereas the peak power, you are looking at an infinitesimally small instant of time, and you are calculating what is what? What is the maximum power? Maximum power will appear when the amplitude is what? When the amplitude is what? Maximum. Do you agree with me or not? Maximum power will appear when the magnitude is what? Or the amplitude of the signal is what? Is constant. But is the amplitude going to be constant for a long period of time or just a short period of time? Just a short period of time. Are you following or not? It's sinusoidal stuff. Yes? And that is why it is rather difficult to what? To carry the, or to measure the what? To measure the power. Now, first of all, what is the power in the carrier signal first? Power in the carrier signal is what? Is this the average power or the peak power? That's the average power. Can you tell me what is the peak power? Huh? Why? Correct answer. Why? Why is it a square? Remember, when we are talking about peak power, we don't worry about dividing by what? 2. Did you get my point or not? You are not dealing with what with the root mean square. You are just dealing with peak power. Yes? What is the peak amplitude? What is the power? A square. Now keep in mind, by the way, when people say a square, I want you to always remember what they mean is a square over r or a square times r. Do you understand that or not? Yes or no? You need to always keep in mind that there is a resistance, and you will see it, by the way, in the midterm. In the midterm, I will give you questions. Don't tell anybody I told you. In the midterm, I will give you questions in which what? The resistances are not 0, which means what? I don't want you just to say the power is the what? Is the voltage square. It's the voltage square divided by what? R. But there won't be any 2. Do you agree why there won't be any 2? I am not calculating the average. I'm taking the what? The peak. What is the peak of a cosine? A. Then the power will become what? The peak power is as if I have what? As if I have a source that is generating constant amplitude of what? A. The power will become what? Will become a square. Clear? So for a single tone, sinusoid, sorry, clear, clear, which means what? What is the power? Two, which is what? Clear, clear. Answer me the following question. What is the power in the unmodulated carrier? Still waiting. I cannot hear you because you are not saying anything. You are not saying anything. What is it? Agree? Agree? Okay. What is the power in the sidebands? What is the power in the sidebands? Where is the sideband? Okay. This is, by the way, what we refer to as what? What we refer to as what? As a mu. Did yes or no? The steer uses what? M instead of the mu. I should have used M. But the universal symbol for it is a mu. It's not M. But in any case, what did he assume? What did he assume the modulating signal is? It's a sinusoid, a single tone. Yes or no? What is the power of this guy? The first one, the first term is what? What is the first term? First term is what? It's a square over what? 2. Agree? Okay. What is the second term? We have cosine, cosine. Yes? Cosine, cosine is what? Is cosine the sum, cosine the difference? Yes or no? Over 2, is there over 2? Okay. What do I have here? AC. Yes? What will be the component? What will be the power in every band? Remember, one more time. By the way, can I just square this and divide by 2? I can square this and divide by 2. This is now the what? What is this? What is this one? That's the envelope of the what? Of the modulated carrier. So A what is it? Remember, this is multiplied by what? Cosine. So what is it? Is this square over what? Over 2. But this square, you need to what? You need to find the power in the modulating signal. Yes or no? What is it? The amplitude of the modulating carrier. By the way, what is the power in the modulating function signal waveform? Still waiting. You are struggling here. Clear? That's a definition of what? Oh, sorry, I forgot. That's the definition of what? That's the definition of the average power. Did you get this or not? Yes or no? Now, if M of t happens to be what? If M of t is mu, sorry. If M of t happens to be what? Cosine omega mt, then this one here, by the way, do I need the limit anymore? I don't need the limit anymore. Why? Because it's a periodic function. I just put what? It's going to repeat itself. What will it be? It will be. Now, this one is what? Mu. So what will it be? Mu square. I'm still waiting. Mu square. You lost me here. Did you lose me? Where the 4 came from? Where the mu came from? Okay, concentrate. You lost me here. The first term is what? What is the first term? A times what? Cosine omega ct. That's the carrier component. The power is what? A squared over 2, the average power. Yes or no? Okay. The power in the modulating signal, if it is M of t, just M of t, is what? Is this. It's called what, for example, P sub n. But I'm assuming that the M of t is what? Is bounded by what? By 1. If it is bounded by 1, in other words, M of t, did I mention this somewhere or not? Hey. Yes? What will this one be? So dt is what? You get 1. You follow me or not? So where is this coming from? This one is coming from because you have what? You have the term here, mu, mu a. So it becomes what? Mu square, yes or no? A square over what? 2. And can you tell me where is the 4 coming from? So when you multiply cosine by what? If this one is a cosine, when you multiply cosine by cosine, you get what? Cosine, the sum cosine, the difference. Yes or no? That explains this one here. So what is the total power? Did you lose me? No response. How do I calculate the power efficiency? How do I calculate the power efficiency of this modulation scheme? Agree? What is the denominator? Agree? Agree? Where this came from? That's the carrier power. And the numerator is just what? Can I factor the a square outside? So what do I get? Agree? No response. Agree? This is the power efficiency. Good or bad? Why? Why? I want you to understand why. Listen to me. For envelope detection, why? I'm still waiting. Why? If mu, remember the cosine, the cosine is what? Plus or minus 1. Yes or no? If mu is what? Is more than 1, and if this happens to be what? Negative. Yes? What will happen to the whole thing? Becomes negative. Yes or no? But I just told you a moment ago that you want the envelope to be what? All parts of the signal to be what? Positive, so that the envelope is above the x-axis. Did you get this or not? Okay. So the mu condition for that is that the mu has to be less than 0, which means what? Clear? What does this mean? One more time, what does it mean? 33% of the time, you are sending what? Useful information. The remaining part, you are sending what? Nothing. By nothing means what? It's just a carrier signal. Clear? It's no information. Yes or no? Okay. Now, let me ask you a question. I'm going to say a statement. Tell me if it is true or false. The efficiency of AM modulation could be more than what? Could be more than what? Actually, it could approach 1. Why? Let's see if you can help me. Could mu be large? Of course, could be large. Mu could be large, and you will end up with what? The numerator and the denominator is what? Is almost the same. You agree? But if mu is large, you are not going to be able to use what? Envelope detection. Your only way of recovering the signal is through what? Coherent detection. Do you understand that or not? So when people talking about the 33.3%, excuse me, when they talk about the 33.3% or 33, whatever it is, percent in the power efficiency, they are emphasizing that you are going to use what? The envelope detection rather than what? Rather than coherent detection. Clear? Okay, good. Now, for the AM signal, explain to me where this came from. Where is this came from for the power? I'm still waiting. What is this? Remember, the M is the mu. Yes? What is the maximum of this guy? What is the maximum of this guy? Remember, we are assuming that M of t is what? Absolute value is equal to a normalized. Yes? What is the maximum value of this guy? A times what? Plus mu. Yes or no? Why? Because the peak value of cosine is what? So the peak value of this one is what? A. The A, by the way, cancels if you are taking a ratio. Yes? What is it? 1 plus what? M mu. No. 1 plus mu, the whole thing what? Square. Yes? That's the peak. Why is that this? That's the average stuff. Did you, I made a mistake? By the way, this is from steer. I did not check it. So I need to check it, huh? What happens when mu equal to what? There is no modulation. The what power? Yeah, and that's why I told you that you need to check this equation. And that is why I just told you there is a mistake here. You need to check it out. Do you understand that or not? Yes or no? That is, I just said it. I just said that but listen to me. Can you tell this one is a scanned version? Yes or no? I just scanned it from the book. So I need to check this equation to see if it is valid or not. Clear? Clear? Okay, check it yourself also and let me know. Can you do that? Huh? Okay, let's put extra credit. 1 second. Extra credit. But this is after the midterm, not before. Derive. I don't want you to look at this. Do not look at this because there are mistakes in here. Derive it on your own. Derive an expression for par for AM signal with single tone modulation, single tone modulation, and plus 1 point. And let's say this is due Monday midnight. Again, 1 point. And the same thing, you email it to me just like you did for the previous one. But did you understand the question? Did you understand the question? I want you to derive it, go through the derivation here, and see if you can get this result. Clear? No response. Clear? Okay. Now, next. What is next? Frequency modulation. First of all, let me ask you a couple of questions. The AM band in the US. Still waiting. It's roughly 600 to what? What is the total band? What is the channel bandwidth? Anybody? 10 kilohertz. What does channel, when I say channel bandwidth, what does it mean? It means when you tune your radio to a certain channel, what is the next channel? The next channel, you will see that it what? Changed by 10K, which means what is the number of channels? Yes? Does that mean that we only have 100 broadcasters in the US? What does it mean? They are frequency reuse. They are going to reuse the frequencies as what? As the phasal, as the spatial separation increases. Clear? Clear? Have you seen the antenna, an AM antenna? Do you expect it to be short or tall? Very tall. Why? This is AM radio. You want the coverage to be what? To be wide. Are you following on that? Okay. Is this a licensed band or an unlicensed? In other words, do they pay money for this? They don't pay money for this because this is for public what? For public use, for public safety, for advancement of society, whatever that means, I have no idea. They just need to play by the rules of FCC about what? Decency and morality and speaking good language. In other words, no 4-letter words and stuff like that over the air. Did you get my point or not? And the FCC review them regularly to see if they are adhering to the what? To the rules. And their purpose is to provide what? Information. In terms of what? And in terms of news, whatever, all of these mumbo jumbo. Clear? Clear?
Do they use coherent modulation?
No. AM radios, by the way, are cheapest possible. Do we agree or we do not agree? Can you get it in a cereal box? You buy cereal, you get yourself what? An AM radio. AM radio, everybody gives you AM radio for free. Just like calculators, which are what? Non-scientific. Do they give it in a bank or say, open an account? They give you a what? They give you a calculator. It's the cheapest stuff. Clear? For
Do they do that because there's harmonic?
No. They do that, my dearest, because what? We are talking about mass production. Mass production. They don't want to make AM radio to be what? Expensive. AM radio is supposed to be what? The cheapest thing. You follow me? You don't want to make the receiver too expensive that people will not be able to what? To receive it. You go under a tunnel. You are driving and you go under the tunnel. Do you still receive AM signal or no? Why? The signal is what? Is amplitude modulation, which means what? The amplitude is going to what? Vary. And because of these obstacles, the tunnels and so on and so forth, and the information is on the amplitude, you are going to lose what? All of it. Whereas on the FM, on the other side, the FM is a what? You go underneath a tunnel, you still can receive what? The FM signal with little degradation. Did you get this or not? Why? Because in FM signals, the information is modulated onto what? Onto the frequency rather than on the amplitude. Clear? Clear? Okay, good. Now, frequency modulation. Let's see if you can help me here quickly. Okay. What is the first thing that we need to do when you deal with frequency modulation? Is to write what? Is to write the mathematical model. So in FM, the mathematical model is the following. X of t or S of t equal to A sub c cosine 2 pi FCT plus 2 pi KF, the integral of M of t dt. Close the bracket. I want you to tell me something. Listen to it carefully. Listen to my question carefully. This is what? It's 0 to what? 1 over t. Listen to me carefully. I will define what KF means in just a second. But listen to me carefully. Is the amplitude constant? And the amplitude is constant. Why? It's the information is on the what? Is on the frequency. Yes? Okay. What is the instantaneous frequency? First of all, this is amplitude constant. Question, by the way, question, is the amplitude really constant or there will be some fluctuations in it? There will be some fluctuation in it, and that is why you see part of any FM receiver is what is known as what? A limiter. A limiter is what? What is the limiter characteristic? Chop it. Did you get my point or not? Yes or no? So any fluctuations, what? Any fluctuations that goes on top, it will what? Cut. To make sure that it is what? Constant. Clear? Clear? Actually, it's not like this, but you get my point. It's like this. Did you get this or not? Certainly. So if it is below that, it will what? It will pass through. Okay. Help me. What is the instantaneous frequency? Do you understand, first of all, what do I mean instantaneous? At any given instant of time, what is the frequency? Is it changing or it's not changing? Of course it's changing. The modulation is on the frequency. What is it? F sub c. So F instantaneous equal to what? F sub c plus what? What is M of t, by the way? Did you say modulating frequency? Signal. I thought you said modulating frequency. Yes or no? Cannot hear you. Okay. This is what is 2 pi. F sub, by the way, what is F sub c? Ah, mistake. Tell me. KF times MT? No, that is the what? That is called the phase modulation. This is FM modulation. This is what? See, if you talk about the phase, where is the modulation? This one is 2 pi FCT. Yes? Did I mess up? Can you factor out the 2 pi? So what remains inside? FC plus what? Plus this guy. Yes? Okay. Now, what is KF? Anybody remember? No, you don't remember. Let me derive for you so that you understand what I'm talking. Let M of t what does that mean? When I say A cosine omega MT, what does that mean? The modulation is what? This A sub M. So what do I have? What do I have? S of t equal to what? AC 1 second. I made a mistake here. No, I made a mistake here. What is the mistake? I factor out the 2 pi. Yes? So what remains here is what? Is FC. But this one does not have t. I need to take the derivative of this. Oh, yes. You should have said that. You didn't say that. Okay. Okay. I need to take the derivative of this so that I get rid of the integral. Yes or no? Need to get rid of the integral. So remove this. So one more time. What is Fi? Fi equal to what? F sub c. And this one also would change. Why? Because m of t is what? Okay, 1 second. Cosine 2 pi fct plus what?
5-minute warning.
Question?
Oh, no. It's 5 minutes left, Professor.
Yeah, now it's okay. Now it's okay. Okay, continue. What is it? AC cosine 2 pi fct plus. What is the integral of this guy? It's 2, and the 2 pi f cancels with this 2 pi. So what do I get? Over what? And this a is what here? This a is a sub m. And then what? Agree? Yes, and what? How do we define? Define a m kf over what? One more time. What is fm? That's the modulating frequency. Remember, we assume that it's a single tone. It's defined as what? Anybody? And beta is called the what? The modulation, FM. Modulation index. What do I call AM, KF? Huh? No, I know there is another name for it. What is this? Deviation. Deviation from what? From the carrier. Remember, we are modulating the what? The frequency. So the frequency of the carrier is going to what? To change. Are you following me or not? Yes or no? Okay. So for example, in FM radio, anybody? 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 When I say plus or minus 75 megahertz, what does it mean? What does it mean? 75 megahertz on one side, 75 megahertz on the other side. Yes or no? Around what? When I say 75 megahertz. So, what am I doing here? Kilohertz. I cannot believe it. 75 kilohertz. Center frequency is almost 75 megahertz. So, plus or minus 75 what? Kilohertz. Yes? What does that mean? What does it mean? Give me an FM channel. Give me an FM channel example. 97? What is this? Heavy metal stuff? What is this? What is the bandwidth roughly? But in reality, the bandwidth is how much? 200 kilohertz. Yes or no? We will see the bandwidth. Anybody knows what we call this bandwidth? Have you heard about this? What is it? What is beta times FM? beta times FM is what? Delta F. Yes? You do understand the delta F, this one is what? 2 delta F equal to what? Did I mess up? No. Two delta F is what? On one side and then on the other side. Each one is delta F, 2 delta F. So what is it? 2 beta times FM. 2 beta times FM. This is the delta F. So it's what? 2?
Professor?
Yes.
We are about out of time. Yep.
Okay, that's fine. We'll continue next time. So it's this, which is in FM radio, roughly what? They use this. I made a mistake? But we'll continue next time.
And this concludes EE 544 on Thursday, March 6, 2014.